Okay, so if people can tell me when they can hear me, I think that we might have a challenge with the out of sync on this, with this particular microphone. So I think it's about half a. Excellent, C. Holmes, excellent. Okay, so I'm going to read through your comments quick. You've been having a nice chat. Okay. Good evening, Corky. Good evening, Artifact. Good evening, Steen. It would be nice to see Brilliant Light Power's presentation. Good day, mate. Okay, so before we get going, I just want to thank Bobcat Sweden. It's because of their support that I was able to put this better solution together for streaming, and it's the first time trying it out live, so we'll see how it goes. But I think there's a lot of improvements I can make. So I think the issue that there might be on this video is that my audio may be half a second out of sync because I'm using a Rode microphone which is USB, and so it's not so real time. So I might look to implement that in a different way, or allow in the software. It does allow for a shift in latency, but I haven't nailed that yet. So sorry if my lip syncing is out. Anyway, it's the visual data that I think you're here for, I hope, and maybe some commentary. Yes, I'm sorry about the 2215 CET. There's normally when I'd like to do the presentation because it is better for Americans, and I just kind of wrote that. I've actually corrected it already. Riandathal, I will talk more about the energy source at another time. There's specific things that were said in Sochi in 2018, and I really need to build the argument on that. It will take some time, and it has extremely challenging implications, and what I need to do is I need to cross-reference what was said then with observations from other, let's put it like this, events which are highly sensitive, but I would suggest that you should go and read or view a presentation and read the associated paper of Xu Wenju and his team in China from 1988, I think it was, to 1999. And he was looking at the effect of three-body alignments, and that is where you have the sun, moon, and earth in a straight line. So you either get a solar eclipse or a lunar eclipse. And he was looking at the effects on sideways movement in metal, using a sheet of metal and then some strain gauges, and observe sideways movement. And this was inspired, I think, by an observation, I think in something like 1954, by, you can go and look at NASA's website, by Maurice Allais. It's a French name. He actually won the Nobel Prize for economics, I think, in, I don't know, much later in his life. But this, for me, is his most interesting contribution. And he had a Foucault pendulum, and during a three-body alignment, it went out of its kind of normal precession. And so you can go and look at it. I think it's If Gravity Can Do This, What Is Gravity? Something like that, the name of the presentation. But he also observed that beta isotopes, cesium-137 and rubidium-87, they supposed to decay at an average rate and an exponent. However, he found that in three-body alignments, those nuclear clocks that were based on rubidium-87 and cesium-137 that were in the shadow or penumbra of the, say, solar eclipse, or outside it or in another part of the world, they actually had differing in time. He also observed that crystallization of a lead tin alloy, it crystallized differently depending on whether it was cooling inside the eclipse or outside of the eclipse. You actually got these linear crystals forming. And then the last point was that he observed that the spectrum from elements changed. And so you can see that time is affected, that crystallization is affected, that there is a gravitational or certainly a force moment affected, and that what's the last one? And also the interaction of photons with electrons in matter to produce the spectrum from atoms. And so these are about as fundamental as you can possibly imagine, and therefore the same factor is playing into all of those hands. He wasn't aware at the time of the work of Alexander Parkhomov, who proved that something akin to clusters of cold neutrinos from the cosmos were causing a variation in beta decay, and that these things were large enough to be reflected and also lensed by solid matter. And so when you take that in context, you have a influence between all of these different factors and some otherwise abundant and ubiquitous energy-bearing structures that rain down from the cosmos on the Earth, that are affected by gravity and influence the nature of our physical reality in every way that we can really perceive it. And you need to go and look at the work of Simon Schnoll. He looked at work from 1950s all the way through to 2012. His paper, or book rather, is available online. And the Russians call this a common cosmophysical factor. And I think what we can conclude that this is in the cosmos. And we know that cold neutrinos are they're in the sort of range of about 2 or so Kelvin. They're left over supposedly from the Big Bang, but they can be made by other cosmic events like supernova and those kind of events. And so it doesn't necessarily have to be a Big Bang. And that if you look at something that I shared in the lead up to the translation of Alexander Parkhomov's book, I had a series of papers that were very, very important with QR codes. And one of those was talking about the cold neutrinos being effectively a single coherent matter throughout the entire universe. And so this energy is available at any point in the universe. And it has a flux. These things are not relativistic in their speed. And I've discussed this before because they are synthesized in great numbers on the sun, but their velocity is insufficient to escape the sun's gravity well. And so they basically go out and go down. And Alexander Parkhomov argues, and I believe quite rightly, that these could account for a large amount of the transmutations that are occurring in the sun and in the corona of the sun. So that's really an aside, but I think this matter energy appears to be accessible at any point in the universe. It appears to be able to be condensed, and the tool that we can use to condense that matter is the exotic vacuum object. And in doing so, and if you look at, I think in my presentation, a couple of presentations ago, I looked at a a historical document by Takaaki Matsumoto, and he was talking about, I think in the 1991 period or 1992, that he had specified that his itonic clusters were containing positrons, electrons, and neutrinos. Now, he didn't specify the neutrinos, and again, he didn't have the understanding of Alexander Parkhomov, which was at that time forming. But if you are condensing electrons and they are going into a smaller area, you can imagine it like PV equals nRT with gases. As you get a lot of gas and you compress it into a small area, the temperature goes up. And you might have experienced this when you are pumping your bicycle tires. The temperature of the tire goes up. And in the case of condensing matter into this coherent ball lightning, and you have this sheath, the energy of the individual particles, or the likelihood of their colliding as they're condensing down, imagine it's the same kind of thing. And then when you exceed a certain kinetic collision speed between either the ions, the nuclei, or the electrons, you will create cold neutrinos. And this is well documented in Alexander Parkhomov's book and papers. And the cold neutrinos are antineutrinos and neutrinos, but these are not the neutrinos that come from an electron capture or required for electron capture or a beta decay, where you get a neutron decaying into a proton and an electron and an electron antineutrino. Those are relativistic. These neutrinos, basically, they're slow, didn't stop, relatively speaking. And I am saying, and will argue with context to the Russian work, that because electrons, and I've argued this before, because an electron can, once you've got these cold neutrinos formed, then you can have interactions, and we know because of the weak force, we know that electrons can interact with neutrinos. But in this case, the electrons and the neutrinos are basically in the same space. An electron can you can imagine a simple equation where you have an electron and a neutrino on one side and an electron and a neutrino on the other side, and they can share energy between themselves. So like an electron can, you basically have an electron and a neutrino on either side, but the kinetic energy, the non-rest mass energy, can be shifted from the electron to the neutrino, or the neutrino to the electron. So if you can imagine you have a force-free torus, and the electrons are spinning round, and as they condense down, they are synthesizing cold neutrinos. These cold neutrinos will be swept up in the vortex of the electrons, and they effectively are moving in the same fashion. And so that's just an aside there. So I really want to get on with the presentation. I can talk about this at another time. So it's in sync at the moment. That's great. Okay. Yes, alchemy will require, preferably, to be alignments of planetary bodies. So I have my greatest insights as we are coming into the spring. So, and that's in the northern hemisphere. I imagine I would be doubly more productive if I spent, my springs in the northern hemisphere and my autumns in the southern hemisphere. And this is clearly described in Space, Earth, Human, Alexander Parkhomov's book. And the reason is that the cold neutrino flux from the cosmos, it is gravitationally lensed, and as the part of the Earth is closer to the Sun, for instance in the northern hemisphere, going the spring into the summer, you actually have a denser condensate of the cold neutrinos, and this would be true of planetary alignments. So it would either be better or worse. But if you had, say, Betelgeuse directly behind the sun, that might be a good arrangement for doing your alchemy. Okay. Okay, so I'm going to get into this. So what are we looking at? I'm gonna switch frames here, maybe, if I can. I don't even know what the other frame has got. That's not what I expected. So we'll go back there. That's just the background. So I don't know why that's not showing the thing that it should be showing. I'm gonna go and no, that's not good either. Like I say, this is a test. I don't know if people read the blog, but I would go and suggest you read the blog on remoteview.com, remoteview.icu, sorry, because that has the paper from 1983, which I think is relevant to the structures that you're going to be seeing today. Okay, so just bear with me. Something went awry, and I need to fix it. Okay. Sorry, this is tedious. Okay, just to give you something interesting to look at. So what you've got here is this brass plate. I'm going to switch the thing to maybe autofocus for the minute, if I can. Okay, so you can see this brass plate here and the structure of the interaction of the plasmoid track. Now you can see these vertical lines here, and actually running through the center here, and you can see the edge of the brass plate here that I showed in the video earlier this afternoon. And so brass is predominantly copper often, and some zinc, and it often has, or sometimes has, lead in it, and it sometimes has some tin in it. And I showed the potential reactions that you can get with those various elements. So leave that there for the minute. Okay, and I'm going to see if I can reconstruct the view that I had earlier. And I don't know why I am not getting it, so you just have to bear with me. Like I say, this is all very experimental. Oh, I know, that's going there. Desktop. Oh, it's really struggling. Huh. You know, it's you have everything correct and then it just doesn't work when you want it to. Sorry about this. Okay, so I'm doing this about face, so I need to put that down the bottom. I'm trying to learn this real time. Oh God. Centre back. How do I do that? Centre back. Okay. Right. It's quite possibly the worst video ever. Okay. So I've got the microscope here and I can move that up and down. And what I was doing earlier is I was drawing on this and to show where you have this kind of, oh no, oh dear, I'm really sorry. I feel like I should come back and do this another time. Lock, right. Okay. So what I was drawing earlier is that when I showed you a little while ago, the edge of the brass plate is kind of there, and this is where this, what I'm maybe suggesting is a magnetic fluid, a condensate fluid, and you can see it has a sort of curved area here, and these are kind of rising up like that. And we've got it again over here, and different heights as it comes in, it's getting smaller down here, and there's a kind of curve around here. Now if I actually get rid of that and go down a little bit, you can see that there's a very strong demarcation here, and you've got a bit above, and maybe I can use the focus on here. Oh dear. Everything was working perfectly earlier. Okay, so why don't you? Ah, there we go. What I've done there is I've used the micro touch focusing, and it allows me then to control the focus level. So what I'm showing you here actually is that there is a curved section under here, and then there's this edge here, and I'm suggesting that you have like a plasma ball structure in here, but like we've been seeing on other VEGA experiments, it's actually kind of like a fluid, and so we've got a ball here, and somehow it's eating into the brass here, and it's building up something above here, and it will be interesting when we look at this structure over here what that is on the EDS, to see whether that's probably maybe copper oxide, or it's some sort of carbon in there or whatever. But definitely something's going on here where it's kind of partially eating in and partially on the surface. And if I cut back to the view here, you can see that, as I said on the sort of introduction video, there is 3 areas here. There's this area here, this boundary area, there's this fuzzy area, and if you looked at some of the other VEGA videos, there was this kind of like fuzzy outline that was outside the overall ball, and depending on the position of the the zoom level of the camera, you would notice that there was a very intense area in the center of anything that Henk was looking at, and then there were kind of a couple of layers, and then outside of the fuzzy area it was just the free space, which is maybe this area here. This is largely unaffected. When we change the orientation of the microscope view, you'll see that this is basically the untouched material. There's a little bit going on in this area. There's quite a lot going on in this area. There's some really funky stuff going on in this area, although I kind of like this area more. And then there's these very deep ravines. And so, anyway, we're going to get to look at that now. So, and I'll just see what you're saying at the moment. What paper are we talking about? Okay. If you go to remoteview.icu and look at the top blog there, there's a paper in that blog. We can talk about volunteering afterwards in a separate video. Okay, so I'm gonna rotate this now. In fact, I have to rotate it all the way around, and I'll get rid of those pieces of rubbish on the screen. And those pieces of rubbish. So, and I need to move this back a bit. Okay. Right. Wow. There we go. Lovely. Okay. So I have this other part of the cathode. So what was being done? Now I need to change the position of the main microscope here. Okay. 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 So I'm going to change what you can see on. I'm going to move this around and change the view again. Okay. So what you can see on here are these markings, and what Henk did was he found that the opening to his reactor wasn't so large, so he put his cathode metals in through this opening in smaller pieces, and then they were stacked on top of each other in certain cases. And so we have another one here to look at in a different session, which you can see here, and there's some interesting things going on there. And you can imagine that if you stack things on top of each other, one would create a line. So maybe if I put that there, it's something like this, or other piece on top of it, but actually more on top of it than here. And so you can imagine that there was some sort of electric field build-up or plasma build-up on the interface between the two. So maybe it inadvertently made some sort of resonant cavity, and it may not have been this piece of metal. In fact, I'll get the entire details, but I think there was a stack of metal of brass plates, and I think this occurred between some brass plates. So there was a gap, but clear either from a previous run or whatever, there was a track, and it kind of used that track and then built up this beautiful structure that we see here. Okay, so okay. Right. Move that one out of the way. We actually have a lot of samples to look at, and so it will be interesting to have other sessions, and you'll have to let me know about what you enjoyed about a session and what you didn't so much enjoy about a session. I'm going to go out a bit. We are at the sort of 50 times view. It's kind of what I want. That's 47 times. Now, if you remember from the side view, we had these channels. And so if I move this around a bit, and we find a suitable channel, and you will see that these things respond very differently to different light. So, being at this distance, you actually get a kind of a larger depth of field, and it would take a lot more time, but I can take high depth of field, so I can take multiple exposures and then build in Photoshop a high depth of field. But what I'm going to do now is I'm going to wipe through the focal plane here. So I'm looking at the top and then coming down to the lower part. Okay, and I think what I'll do is I'll actually bring up the paper on my remote view.icu. Because I took a screen grab from that particular paper, and I think it's quite relevant to just drop that in there now. So we always know that these exotic vacuum objects, these ball lightning, these coherent matter structures, they appear to have a magnetic nature to them when they don't always necessarily have a charge nature to them. Okay, so what we're looking at here, if I go to my little note here, this area down here, if I can do it, this area here, this looks like straight brass. I mean, you'll see when you zoom in, there is some affected nature to it, but it's if you can imagine, it's almost like it's sucking up the raw material from here, and this is kind of like the scoop. And if you can imagine, you've got a sphere in here, and there's 50% of it is below the watermark, and 50% of it is above, and that might not be precise, and a lot more study needs to be done. But when you go around this area, predominantly they are all of the same kind of scale. And what I'm going to do here is I'm going to start throwing on some measurements, so you can get an idea of what we're looking at in terms of scale. So the Dynalite Edge 3 that I have here, this is a 5 megapixel camera, and so what I'm gonna do is focus on these flat areas here, flat area here, flat area here. When I say flat, when you get an area that's quite large, this bit and this bit are actually falling down, and there's a bit of a trough here. So you can see other areas that we'll look at where this is more obvious. Anyway, okay, so let's get some measurements on there. So I will just do some 2-point measurements. So let's have a look at a typical channel width. So we've got a channel from here to here. So that's a 1.411 millimeters. We can, oh, it's done it again. Okay. Have another one here. .2 millimeters at that narrow area there. Okay, 1.6 millimeters. So the structure may be a similar of order of magnitude to the 16 millimeter structure that we saw on the Hutchinson fracture sample. So now this bottom part of the trough here, where it's kind of looks like it's mostly the brass. We're looking at 0.6 of a millimeter here. Okay, so there's some measurements just to get you going. I'm going to clear those. And I'm going to switch to the view of the paper. Okay, so this is this paper, and when you compare the structure that we are currently looking at, and I'll bring in another layer onto that. How do I do that? No. And I'll focus that. So look at this area here. I'll take the camera out and we'll zoom into this a bit. Somehow. Anyway, let's zoom into that up here. Okay. Now, do we think that what we are looking at on that paper for the magnetic fluid is similar to the kind of structures you are seeing in this affected electrode here? Now, it is a cathode. It's not the anode, obviously. So there we go. And there's one thing that's a little bit distinct. So when we are looking at a magnetic fluid, the lines all, the channels all sort of are a similar sort of diameter. So I'm saying it's something like this, as we're seeing here. Where I divert from that slightly is that you have these end pieces here, like this one here, and maybe this one here, and in a dielectric fluid they're kind of separating out. But I don't see this great change in channel width from the center to the outside, whether you're looking black white or white to black. It really does seem to be this one over here, and variants of at different scales. This is different gaps and different fields. So if I clear that again, this one is low field, large gap. This is high field, large gap, and high field, small gap. And if you actually look at the sample, and I can move that into position maybe. Nope. Oh, that's terrible. I wonder if there's a different field here to here, and that corresponds to the type of different structures you're seeing. Maybe there's something going on there that we can think about. Anyway, so I'm going to start looking around this in a little bit more detail. I'm going to find you, whether you're still there. Are you still there? Okay. And I want to focus that. Okay, so when we're looking at this area, there is such a large change in elevation, as it were. And these kind of remind me of the Tepuy in Venezuela and going into Brazil and French Guiana. They have these very flat tops and these broken ridgy sides, but they are quite stunning. You see how clear that channel is? It's like basically almost looks a bit like raw brass, but I suspect it isn't. So again, I'm panning through the field, depth of field there. Now, at this magnification, I want to go and look at something that I had on the video earlier. Actually, well, whilst we're here, let's have a look. We've got something here that's quite hexagon-like. So, and actually, I have up in this top left-hand corner, I have a magnifier, so I can actually go and look at things. You see, a very hexagonal structure, and you're going to see a lot of that. There's another similar kind of hexagonal structure down here. I want to go and find that little area that I had on the trailer video, and it's all the way up here somewhere, I think. Here. Now this is really interesting, because I imagine some of this is like copper oxide, and what you're seeing is if you look at the main channel. So I'll draw here. This is the main channel over here. So I'm going to go over to the main channel. So you can see this is the main channel because it's kind of really deep, and we are seeing the brass here poking through. But it kind of gets to an end here, and you can see that there's some height here, and there's like a spillover into this area here. And it's kind of like this built-up area. Now, this may be some copper oxide or some other structure, the high plateau areas. But there's actually a cut through here, and it's like whatever this coherent matter was here, there was a bleed out, and it kind of spilled out and came out, and it's like a higher plateau area that we're seeing here. And it's absolutely stunning, and you're going to see in a second. I'm going to change the light, so I'm panning. Now you can see I've gone all the way down here, and now I'm in the focal plane of this area over here. Okay. Now I'm going to shift the focal plane, and you're going to see that we are in. If it's going to let me, we are in the focal plane of the spillover area here. But we're still not in the focal plane of the top of the peak, as it were. So I need to cancel that. And we'll change that again slightly. So now we're in the focal plane of the bottom of this area here, and some of the outer ridge areas here. And then if I keep going, I'm now at the focal plane of the top ridge here. and the top ridge here. Okay. Now you're going to get a very, very good look at the structure of this, because what I can do is on this microscope I can actually turn off individual lights. So if I turn off the lights, you can see this beautiful, I'm going to turn on the intensity here. It's just stunning. It's just absolutely stunning. And the interesting thing that I notice here, so I'm going to go around and just show you what it looks like. I'm going to turn off that light and that light, so you can really see the bowl of this structure. Turn off this light, and then this light. Now, if I go back to this one, and I show you again, there's this structure here, and then you can see that there's kind of like a radial array around here, and it's kind of like poured into here. And additionally, there is radial structures going round here, and there's radial structures going round here. Now, this might all be stress related or field related, but that is what you're seeing there. You know, I just love it. It's just beautiful to me. Whatever floats your boat, I guess. Okay, so I'm going to have a look at your comments here. It is like a volcanic landscape, but you've definitely got a number of layers. This area over here, down here, is the plateau, which is nearly at the level of the brass sheet by itself. This is kind of like it's building up to here. This is a peak around here. This is a peak around here. This is a kind of almost like a caldera in here. But this is this smooth trough here, where you can imagine this plasmoid structure. Now, if you looked at the things that we saw on Sapphire, but also more importantly on the VEGA experiments, you can get these coherent matter structures, and they actually build a whole structure, and it's bled in there. But I'm surmising that the main focus came from here, and it kind of breached this edge of its own node, as it were, this bit here, and it flooded into this higher plateau, and then bored out this new structure here that we're seeing. And let me cancel that as well. Okay, so I'm going to again flick around these lights, because it's quite special to be able to see the form here. Look at that, it's just great. Now I can use the microscope here, because the resolution you're seeing this at, it's actually very high resolution. So what I'm going to do is I'm going to take a picture here and I will be able to share those pictures. So I'm going to take each of these pictures here, and I will share those in the blog on remoteview.icu afterwards. And this one there. Okay, so I'm going to dial down the brightness on that, so you can see you get a much flatter view. Now the other thing is I can actually play with the polarization here, so you end up with a much flatter view if you do that. And in this level of polarization, you are losing the reflected component. You're getting the kind of diffuse component of this. And again, I can turn off the lights here and pump up the brightness. And this is kind of your diffuse look. It looks like something on Mars, doesn't it? That red color. Beautiful. I'm going to change the focal plane down to the bottom of the trough here. Okay, and then I'm going to do one more focal plane shift to go all the way down to the bottom of the main channel there. You see how much further down it is. It's really gouged out of the surface. So you have to have some patience to do this. Some of the images I've shared in the past have taken a long time to put together. You see that in that view, we're getting so much shading here. You can really see how high this ridge is. Very, very high ridge. Okay, so I'm going to dial the brightness down and I'm going to turn all the lights on. And I'm going to come back up onto the top focal plane. Okay, so I'm going to just look at a couple of other areas at this magnification level, and then I want to look at some of the lower dimensional features, but at around about 220 times magnification rather than this 50 times magnification. So we'll just have a look around a little bit more of the main channel structures here. Now, I do expect a lot of these to be copper oxides, for instance. But here you have channels that are kind of adjacent to each other. And this is very much a brass color. And this is very much like a tin color. And so I would be very interested to find out whether this is significantly different elementally to this. And you're going to see other things that are very curious. But again, you see these incredible radial structures going around, all the way around these features. And you can also see, depending on maybe the polarization, if I change the polarization here, and I will need to change the brightness. On some of these structures, you can see you can actually see ridges going around the outside as well, like it's almost built up in strata layers. Oh, it's just lovely. Thing of beauty. Okay. Maybe change our focal depth there. So we go down to the bottom of the pit there, and now we're going to come up to the ridge area. Now look at the top of this. We actually, this area we have some sort of dimple in the top here. It's almost, and it's got its own radial structure around it, around the outside. Look at the radial nature on that. I mean, it's just beautiful. Look at that. And again, you can see there's a top bleed out here, and it's gone to a slightly different level. These are just the macro features. You are going to be loving the small features when we get to them. And ooh, it's gone past my curfew time. I might have to do this again tomorrow, guys. I'm really sorry, but I might have to do this tomorrow. There is so much to show on this sample, particularly at the micro feature level. The micro features are very, very, very telling. I'm sorry, I've left some rubbish on the screen there, and I couldn't see that. Sorry. I left some rubbish on the screen. Sorry. Okay. Look at it's just stunning. Oh, I'm going to take a bunch of shots of some of these other areas here so that I can give them to you another time. So let's take a shot here. This is quite nice, isn't it? I'm looking at the bottom of the channel depth here. And I'll come up to the top. Oh, Jason, you wait till you start seeing the small features. Oh my God. Oh dear. This is such a thing of beauty. It's such a thing of beauty. Maybe before I run out the door, I'll show you some small features. So let's change the magnification level here, and I will zoom in to a larger area here. Let's find something that looks really interesting on the large features. So let's, I don't know, over here. Sorry if this is making anyone feel sick. Okay, this looks nice. I think maybe. Okay. Now when I zoom in, I'll need more light because of just the way it works, because we're looking at a smaller area, so I'll need to pump up the light. You see? It just really looks like a, you know, the edge of a tepui, actually. Go and have a look at tepui. I had the pleasure of flying over one when I was younger. Look how deep that is. I go right the way down into the pit and come back up onto the top. And I'll change the specularity here. I'll change the specularity and bring down the brightness. We get a different look at it. Okay, so look at the bottom here of this pit. Yeah. And very, very strong demarcation here. And then coming up to the top. What you can do actually is you can take a number of photos like this, changing the depth of field, or the focal point rather. And then I can assemble those into Photoshop to create a high depth of field image. Takes a bit of time, but definitely worth it. Right, I'm going to go and show you some features in the spill zone. Now, this is much kind of like flatter area, so we can see features with less focal changing. Okay, so this is the area outside. If I actually turn the, if I switch to this shot and I turn the light off, you can actually see what we're looking at. Right, when it updates. Why is that not updated? It should turn, oh, that one. There we go. So, so we're going to look at the spill zone, and that is the area here. Let me see if I can draw that. This area here. I'm going to have a look around in that kind of like area around the outside, maybe over there next. And I think what I'll do is I'll come back and do another session tomorrow, because there's so much to look at in these areas. It's going to be a lot of work. So turn the lights back on and switch back to here, and let's get it in focus. So we are, let's change that to a bit more. Now, this is very different what we see in this area here. You've got these little lumpy bits. And these little pits, and you might recognize these little structures over here. And possibly I'll need to change the polarizer to pull them out. So you can see these round, this is a ball on top and round down here, these rings with a spot in the middle, and they're generally a wide range of sizes. Let me turn the brightness up a little bit and adjust the polarizer. Like I say, this area is quite flat by comparison. So over here is your trough. This is our raised area, and we're coming down into the flat area. Now look at these. Look at them. Oh, ring spot, ring spot, ring spot, ring spot, ring spot. Oh dear. Ah, look at it. Ring spot, ring spot, ring spot. Oh, it's just beautiful. Oh dear. Now, look at this bead chain here. Look at this bead chain. Look at it. Look at it. This is when I want it to do the 2 times. It has a 2 times function, because you can actually see the movement of the plasma around. Now, I don't know if you can see in the magnification in the top left hand corner, but you've got a sphere here, and then it pulls underneath and then goes into the next sphere, and then pulls underneath and then goes round here. Now these are kind of like joined together, like you see just on the VEGA on a bigger scale round here, and then it goes into the spots, and the beads, this chain of beads going around. Okay, and I'm actually, there's top left hand corner where I'm doing this zooming. Yeah, and you are going to see this all over here. Look at this bead chain here. Now it'd be interesting to see what is on the boundary of these things. So we have this, so I can get that better focus for you. Spot, 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 spot. And I don't know whether this is what Shoulders called wildfire. And it's kind of like it's eating across the surface. And there's many of these. Many of them. I mean, there's, like I say, we'll have a look at this area in great detail. Now, if you want to see an area that has not got anything done to it at all, this is kind of what it looks like. It's just a crisscrossed piece of brass with rubbish on it. And you suddenly go into this transition zone and you start seeing, look at this little plasma channel here. And on the boundary, you have these spots. And they're balled up material. Now, yes, you could argue that there's a cathode spot and it's run down this channel and it's melted the material. But it's the nature of these things, the shapes of them. These are all over the place, Lovely ring spot there. Look at that. Here. Is that a hexagonal or a pentagonal structure around it? Many of these. Now, the other thing is, if you go and look at the blog, I show that you can get a very large number of isotopes synthesized from... I'm going to change the... Is that changing the focus? What's going on? No, frame rate. It's having issues. Okay. Yeah, so it's actually a little bit different on the other side of the structure here. Now look at these areas. This is kind of very shoulders-esque, and I need to change the polarization on this to give it the you need the specular glint to see that the metallic kind of globbiness going on here. And plasmoids will convert metal into, or it would seem, into a very liquid state without necessarily being at the temperature it melts at. But of course you have copper in here, and you would imagine a plasma could easily get copper to its melting point. Zinc, lead and tin all lower temperatures than the copper. I'm going to change the lighting on this so you can maybe get the idea of the geometry. Actually, look down there. It's a very good hexagon ring spot there. Perfect spot in the center and a perfect hexagon around the outside. Like I say, you can easily spend a long time looking at this sample. Okay, so what are we looking at here? I would love to see the elements that we have on this. Sorry about the camera there. That camera is having issues. Maybe if it was zoomed out a bit. No, it's doing something. Okay. Here's an interesting one. You've actually got a square structure here. Really, really square. And and then down here you have a pentagon. And this is, you know, I talked about this in my SWIFTBIC presentation about how cathode spots arrange themselves. This self-organization process. And again, here, this one's more pentagon shaped, maybe even a septagon. This one's more hexagon-like. Really rich area here for Evo strike marks. So this is a shoulders kind of wildfire area here with the little spheres on the boundary and lots of ring spots of different scales. That's a really good hexagon there. Many strike marks here. And you only see this detail outside of the main area, the big channel. So this is in the boundary area. The boundary area is where you see these many Evo strike marks. Again, we've got is that a septagon? I don't know. 1, 2, 3, 4, 5, 6. No, it's a hexagon. Look at this. Look at this. Oh dear. Look at it. It's so beautiful. Look, this one here. You can see you've literally got an Evo here. Now, was this splodge here that birthed from this Evo, or was this gave birth to this Evo? Is it who's the mother, who's the baby? Look, beautiful hexagon there, hexagon here, there. Look at a dual one here. Oh, it's just beautiful. Look at this one. Oh dear. Oh, I'm going to take a picture of that. It's just breathtaking. And I'm going to change the lighting on it so we can get some of the geometry. Okay. So it looks a little bit bubbly, but and these may be uppies rather than downies. Damn it, I'm going to have to go. Oh. Damn COVID. Damn it! Look at these bead chains here. Some lovely melt areas here, look. Okay, so if people are willing to join me tomorrow evening, I will have a look at more of this sample. Again, a unaffected area looks like this. It's just a bit scratchy and dull. Let's get that in focus. This is a raw area, so you can see it's very markedly different from this. Is kind of like just on the boundary, there's some kind of effects going on, then we come in and there's more of these sort of wildfire areas, and then we come into the main kind of boundary area and it really gets a bit messy. It's going to give you a sneak preview of some stuff on the other side of the main channels, because that's quite stunning. So I'm going to go over there now. It's like yin and yang. If I can get to the right area. Absolute pandemonium over here. And I can get to the right area. Anyway, now this iridescent area here, we've got lead in there, and titanium is often produced. Titanium is something, or thin films of oxide layers can produce these kind of iridescent areas, and so I'd be very, very interested to find out what is the elements comprising of these areas up here. Okay, I'll have a quick look at your commentary. Yeah, I do expect to see transmuted elements, Gordon. I expect to see a lot of copper, obviously, but a lot of carbon as well. Okay, so I think, guys, I'll see you tomorrow. I will. You can discuss things. It's open chat on remoteview.icu on this newsletter, so you can go in there. If you're a subscriber, you can go and comment on what I have put up there, and maybe tomorrow I will layer up some of the images that I've taken and post those as well. because it's nice to have the full depth of field for some of these images. Area down here, it's lovely, just lovely. They're very gloopy down here. Look at this. That's with the polarizer completely flat, so there's no specular reflection. There's a trefoil here. Whee! Oh, there we go. All right, so that's your lot. Thank you very much for your time, and I will hopefully see some of you guys tomorrow. Bye for now.